Okay. Hi, friends. I'm Maddie. Welcome to Science Side Up, and I'm happy you're here today. This is just going to be a brief little video. I've got my coffee. Oh my gosh, my Blue Yeti mic, which is right here, doesn't work. And I can't shut down my system to restart it to make it work because I'm actively running some code for dissertation stuff in another window. So also my internet might cut out and so this recording might be choppy. Who knows? Because I'm using Streamer's recording feature because it's easy. Yeah. So, oh my gosh, updates, life updates. It's been half a minute since I've been able to get on and chat with anyone. Um, so in the middle of my dissertation, my defense is it is currently January 30th as I record this, and my reading copy is due April 1st. So that's fun. That's fun. And then I'm going to defend at the end of April. I don't have the actual date set because this is also this week is the American Meteorological Society's annual conference. So that's where my whole committee is, and they're busy and stressed and tired. It's also like the second week of classes, which I'm barely conscious and cognizant of because I'm only enrolled in like 2 research hours, and my life doesn't change whether or not classes are happening. I'm just writing. Um, Turns out writing your dissertation while having a now almost 18-month-old is a lot. Who knew? Who knew that that was going to be a lot for me? And I've been dealing with a lot of burnout, just like generally. And so I am like, I've got all the support I need, and I'm working on like learning more about myself and how do I help myself not get so burnt out and maintain connections with people. And I wanted to make a video for the first time in a really long time today. I think I've been dealing with some burnout for a really long time. Um, and yeah, if I'm being fully honest, there was oh my gosh, around the time baby was born, like really considering dropping out of my PhD program. Then I had a baby and that was my whole life. And then I was like, oh no, I don't want being a mom to be my whole life. I love being a mom, but I don't want it to be the I don't want that to be the most interesting thing about me, right? Baby is I could talk about her for hours. She's awesome. Right, but I'm like, but I am also a human being with interests and ability to contribute to society. So it's yeah, that's where I've been at. Um, but like I said, I had a desire to turn on a camera today, and so I'm going to try to do that. Um, and I thought what we could do was something that I find deeply enjoyable, debunking pseudoscience, right? Have I prepared anything? No, of course not. Why would I do that? The joy of debunking pseudoscience is discovering it live. But I thought what we could do was actually read something from the Answers Research Journal. Um, and I say that so with so much sarcasm. I don't know how to explain to you how not a research journal this is. Um, yeah, it's not. It's not. Listen, I am reading and citing and things, all types of papers right now, right? Because once again, writing my dissertation, that's a thing that I'm doing right now. Again, I'm able to record this because I have childcare at the moment and I have code running in the background, and I can't really move forward until that code is done, right? So that's the task I'm on. So I'm like, oh, okay, I've got 5 spare minutes. Let's jump in and do this. Um, so what I found, let me see if I can um, share screen, select window or screen. Ah, there we go. Beautiful. Um, Sorry, I don't have any of this pre-set up. That's just how things are. Um, it's chaotic, and I'm not a professional. My YouTube channel isn't monetized anymore because I haven't uploaded enough. And allow. Okay. Okay, awesome. So I should, let's see, can I do this now? No? Present? Share screen? Hmm. 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 Okay, hold on. We've got this, but I'm definitely not sharing it. You guys can't see it at all. Anyway, so Answers Research Journal, because I found some stuff in my realm of knowledge. Um, so so I'm working on my PhD in atmospheric science, technically meteorology, but these days there's effectively no difference between those two fields. It used to be that, ooh, okay, here we go. It used to be that meteorology was like short timescale processes and atmospheric science was long timescale processes, but that's not true anymore. Um, now they're now they are just the same thing. Um, so mostly the different names are kept for like historical reasons. So University of Oklahoma, where I go to school, historically has done those like severe weather storms, stuff like that. But now they do everything. I study the Arctic there. Um, so yeah, so I have a strong background in obviously atmospheric science. I also spent 4 years as an instructor in the Navy teaching nuclear physics. So I know a whole lot about how nuclear reactors work. And also, my bachelor's degree I double majored in math and earth atmospheric and planetary sciences. And I focused on planetary sciences. So I have that like more than your average bear knowledge of just kind of geophysical processes in general. So for me, like when I tackle young earth creationism stuff, I look for geosciences because that is what I know about. I know things about geosciences. Um, yeah. So, and the heat problem is kind of one of my favorite things because it's very silly. And so I thought this is a well, four of these parts have been written. I read ahead a little bit. So I found all four parts and I found a few other articles in this Answers Research Journal. So I thought maybe we could do a journal club. A journal club, if you're like a grad student or a professional in a field that actively publishes stuff in science journals, is where you get together like periodically and usually like read a journal article together like on your lunch break. It's supposed to be low key way of keeping up in your field, right? So I thought that's what we could do. I thought we could do a journal club. So we would get together. By get together, I mean I would either live stream or pre-record like I'm doing right now because it's a Tuesday at 10 a.m., right? Y'all are probably busy as I'm recording, but I have 10 spare minutes. So, and we'll just read and debunk stuff as we go. So, like, I'm not gonna have stuff pre-prepared, but as we find things I don't know, I'll look it up and we'll go from there. That's my plan for today. So the heat problem, by the way, Erica Gossip Gigabin has a really great video on this. So the basic problem with the heat problem is that uh, there's two big processes that a lot of time young earth creationists try to jam into the single year of Noah's flood for reasons. Um, One is all motion of plate tectonics. So the basic ideas, and this article is going to talk about catastrophic plate tectonics, which is this idea that basically during the year of the flood, you have Earth's plates moving around at race car speeds, which is one, frankly, preposterous on its face. But two, if you cram um, frankly, a few billion years of movement of the plates into 1 year, then the amount of friction, right? The heat from the friction generated by those movements matters because it's not a big deal if you let that happen over 4 billion years. But it is a big deal if you make that happen in 1 year, right? Um, so that amount of energy alone is enough to fully melt the crust. So that's part of this heat problem, right? There's enough energy, there's enough heat being produced by these plates just moving around. Again, it's just friction, like when you rub your hands together, right? Um, but 4 billion years worth of it crammed into 1 year, that's a ton of energy. Again, that's enough to melt the granitic crust of the earth. Um, and then there's a secondary problem, which is, and this was also like boil off all the oceans, right? It's just liquid magma. Um, the second problem is then uh, accelerated nuclear decay, right? That's a creationist term. That's not a real thing that has ever happened. Let me rephrase, there's no evidence to suggest that there has ever been accelerated nuclear decay. According to all things we can possibly test, um, decay constants for spontaneous nuclear reactions are constant, and they have never changed, and there is no process by which you can change it, no natural process by which you can change it. And so if these were changed by, say, a miracle, right? And we had during the year of Noah's flood, all of these like radioactive materials decaying super fast, to so that we get the apparent ages, right? So that when we measure radioactive isotopes to date things, we get the ages that we see, right? Um, if that were to happen, that's also more than enough energy to melt the granitic crust of the earth. Right? So both of these processes by themselves would cause molten earth, right? That's the problem. That's the heat problem. It's a very big problem. And so this is kind of structured as a what's it called? Like a review article is how this is sort of structured. So let's get into it. Let's read it, and see what happens. We won't go for super long. Honestly, I'm going to check my code in the middle of this. So if I look distracted, that's what's happening. You just can't see that screen. Okay. So this is um, okay, heat problems associated with Genesis flood models, part one, introduction and thermal boundary conditions. Cool. Um, this blows my mind. How am I? Sorry. This is chapter 7 and 8 of Genesis. Those are the first words of your paper. Um, uh, that's not how, I guess, maybe unless it's like biblical studies, that's the only field where quoting scripture would be an appropriate introduction. And this is not biblical studies. This is supposed to be like a geophysics paper. Anyway, all right, let's read the abstract at least. So the Genesis flood must have produced drastic geological changes involving extremely energetic processes, which must also have generated an enormous heat load. I fully agree with that sentence. If the Genesis flood occurred, these things must also be true. Yet, since the inhabitants of the ark and many aquatic creatures survived the flood, stepping into that worldview, right? Like if the Genesis flood occurred, then these things are true. The heat must have been removed without raising temperatures beyond biological endurance limits. Yeah, absolutely. Earth is not currently molten, so where did all that heat go? This is the first in a series of papers intended to identify and, where possible, to quantify the most important sources of flood heat. Here we review the thermal state of the Earth's mantle, crust, and oceans, both now and in the recent geological past. Note that that recent there is going to be a little misleading because in secular, right, in normal science land, um, recent geologically is like tens of thousands of years, right? If a geologic process takes a 10,000 years, that's rapid. That is so fast. It might as well be the blink of an eye. So we're talking. So if he says recent geological past, I think he's meaning 100,000 years at minimum. But obviously he means like hundreds of or maybe 1,000 years. But that's neither here nor there. Um, and take note of mantle heterogeneities as tracers of its tectonic history. So heterogeneity, that's going to be a term if you're not familiar with it. What that means is uh, where things are well mixed, right? So if you have something that is homogeneous, a material is either homogeneous or heterogeneous. So homogeneous is like everything is one thing, right? So I have all my carbon here, all my silicates here, right? Um, Heterogeneous is something different. That's all mixed together. Um, Extensive temperature records based on oxygen 18 content of marine fossil shells indicate geologically recent ocean floor temperatures not exceeding 13 degrees Celsius. Um, yeah, so the amount of oxygen 18 that's in the ocean is so like the ocean like uptakes oxygen 18, right? Water is H2O. And that is actually proportional to temperature. So we know that. But that's kind of interesting because ice core data goes back really far. I wonder how far back that goes. So let me um, switch to sharing something else. Let me just share my screen. Um, that's not the right button, Maddie, silly goose. Okay. I'm going to open a tab and I'm going to go to present and I'm going to share screen and I'm going to select a window. No, I want to do Google. Okay. I'm remembering how to do this. Oh, maybe I do this. This might be terrifying for a second. Haha, there we go. Okay, so I'm going to Google oxygen 18 records. Paleoclimatology, the oxygen balance. So this is a way to measure, this is a paleoclimate tool because it tells us, we drill ice cores and it tells us about temperature going back in time. I just want to know how far back, actually, let me back up. How far back do oxygen 18 records go? Okay. 730,000 years. These, sorry, that's really funny. That's really funny. Oh my gosh. Okay, let's just make sure that that was the answer to my question. Oxygen isotope ratio is the first way used to determine past temperatures from the ice cores. Isotopes of atoms of the same element. Blah. We know what an isotope is. You don't know, my audience. NASA climate science investigations. Um. Do 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 do. Uh. Okay. Okay. No, I just want to know how far back this record goes. Next page, maybe? Ocean sediments. Oh my gosh. No, you're not answering my question quickly. Well, let's take a look at this Britannica article. Okay. Long core samples taken in portions of the ocean where sediment rates were high, generally continuous, where water temperatures change were relatively small, and have revealed a long record of oxygen isotope changes that indicate repeated glaciations and interglaciations going back to the Pliocene. Okay, so we have a record of temperature that goes back to the Pliocene. I don't know when the Pliocene was. When was the Pliocene era? That's even worse. That's even worse. Oh my goodness. Okay, sorry, stop sharing so we don't get the infinite screen. So yeah, according to this article, he's accepting a method that we can use of a record that goes back over 2 million years. Um, so that's fun. That's fun for us. So he's using. So this data apparently is okay to use to measure, the last 6,000 years, but the same record isn't okay to use for the last 2 million. Fun. That's really funny. Okay. So all models of the flood and its aftermath need to take this limit into account. Cool. So we have a thermal boundary condition, right? That was promised in the title of this plus 13 degrees Celsius. A recent attempt to model ocean floor cooling within a biblical chronology by invoking a transient subsurface heat sink, which is a baffling concept. We'll talk about why. Okay, let's go ahead and talk about why that is. That's a baffling concept. Checking my code real fast because, guys, writing a dissertation is awful. I don't recommend it. Like, I want to be a professor when I grow up, so I need my PhD, but like, don't get a PhD. I'm working on not hating everything. Cool. Okay. Sorry. Transient subsurface heat sink. So you guys have been to elementary school. You know that the Earth. I wish I had like a interior model of the Earth I could just grab, but I do not. Ooh, I have a fidget toy over here though. That's not going to help with this particular problem. That's just going to help me fidget. Where's my fidget toy? No, it's gone forever. It's gone. I don't know where it is. I'll never have a fidget toy again. Okay. Um, so the shape of the Earth, right? The crust, very, very, very thin silicate material. And then the Earth's mantle, again, silicates. Um, uh, and the Earth's mantle. So if we could dig down and look at it, the mantle would appear solid, right? But over geologic time, tens to hundreds of thousands of years, it behaves as a fluid. So it is convecting, but convecting very slow, proportional to like human time spans. Um, Below the mantle is the liquid outer core. So that's molten iron and nickel, right? And then below that is the solid inner core, also iron and nickel. And so the Earth formed like this because when you have something Earth sized, if you just bring together all of the mass of the Earth under gravity, that is enough energy to fully melt all of it. So when the Earth first formed, it was a molten, melted liquid sphere held together under its gravity. And then that what happens when things melt, right? That allowed it density sorting. So iron and nickel went to the core, and then the silicate material floated on top as everything kind of cooled. Again, it's sorted by density, which you can do when you're a liquid. Um, so in the mantle, by the way, the mantle is very hot. Um, uh, and is warmed because there is radioactive. So the mantle, there's a lot of different heat transport going on in the mantle. One, like a lava lamp, the bottom, if you will, of the mantle touches that liquid outer core. So it's touching a heat source, just like a lava lamp, which then cycles it up to the crust, which is relatively cold, and then comes back down, right? So we get these convective cycles going on. Two, there are a lot of radioactive materials inside of the mantle. So there's more radioactive materials in the mantle than there is in the crust, like by percentage. Pretty sure. You might want to double check me on that, but I know there's more there. Um, Uh, and then what happens? Okay, yes. And so that's also adding heat to the mantle. And then we also like lose heat of the mantle by conduction. So just the top of the mantle touches the crust, right? And so yes, the mantle is in fact warmer than the crust. And so this idea here of, and again, we've never reached the mantle, right? We've never dug a really deep hole and looked at it. This is just stuff that you can measure mostly with seismic waves. Um, and then you can do computer models and stuff like that. But if you it was noticed back in like Lord Kelvin's days that if you dig down, it gets hotter. Um, that was he measured temperature changes in mines all across the world, and he used that to estimate the age of the Earth. But he was assuming uh, uh, conductive heat loss only, and so he was like, oh, okay, if this is the surface temperature, as we go down, it gets warmer. He assumed a constant linear trend to the center of the Earth, right? And then, so it's like, then he assumed that, like, okay, the center of the Earth, that's how hot the whole Earth used to be. And we've been losing heat at the surface via conduction for however long. Mm, click, click, clack, calculate a few things, and bada bing, bada boom, this is how old the Earth is. Let me, I'm not going to share the screen, but let me Google how old did Lord Kelvin think the Earth was? So he thought famously that it was between 20 and 400 million years old, um, which was this was in 1862. He underestimated because he was only considering conductive heat loss and not considering how the mantle is reheated. Anywho, and assuming again that linear change, he didn't account for the difference in material, right? Iron and nickel is different. Anyway, so it's going to have different material properties than the silica material of the mantle. So that was a long way to get back to this one little phrase that is a transient subsurface heat sink. Okay. Um, so we're going to have, somehow we're going to need to have the mantle uptake heat from the crust, right? Reverse the process. So that sounds hard. Now, if you're hot enough to melt the crust, then yeah, that's going to be a heat sink, right? Because the crust is now hotter than the mantle, and so the mantle is going to try to uptake some. That would be really interesting. How would that work? Sorry. Okay, let's keep reading. Um, Okay, so a recent attempt to model ocean floor cooling within a biblical chronology by invoking a transient subsurface heat sink along with rapid oceanic plate movement was unsuccessful, suggesting that important, hitherto neglected geophysical effects may need to be included in the future. So they tried to make a model that took this stuff into account and it did not work. And they need to figure out another way to remove that heat. Inventories of heat producing radioactive elements estimated from rock compositions and from geoneutrino measurements are in broad agreement, lending confidence to the anticipated process of estimating the heat load due to accelerated nuclear decay during the flood. Sorry, that made me laugh. That's not a real thing. What is geoneutrino measurements? Let's find out, shall we? Um, yeah, let's find out together. Geoneutrino. That's a fun word. Geoneutrino. What is that? A geoneutrino is a neutrino or antineutrino. Oh, okay, cool. Um, okay, so it's a neutrino or an antineutrino that's emitted in the decay of a radionuclide naturally occurring in the Earth. So let me explain what that is real fast. Oh, I'm so sorry. Hmm, I'm not sure you guys actually saw me Googling that, but I read it and I've got a weird, uh, thing. Got a little message I wasn't expecting to see. Okay, but here's the paper again. So geoneutrinos. During let's see. The one I remember specifically is beta plus and beta minus decay, about when neutrinos are emitted. So basically, so a neutrino is just it's a subatomic particle. They're kind of cool because they're very, very, very light and they interact with almost nothing. And so that means they can travel really far distances, right? Because the more a particle interacts with matter around it, the shorter a distance it's going to travel, right? Because it's going to be like bouncing off stuff and slowing down and stopping, right? Um, the neutrinos are pretty cool, because oh, good, okay, my code is still running. It's on step 2. It's completed step 1 and is on step 2, so that's excellent for me. Um, so you make a neutrino when a neutrino or an antineutrino when you destroy an electron or a proton. Proton or neutron. Sorry, not electron. Okay, so in beta minus decay, you have an element, and in the nucleus, I've got to make sure I say this in the right direction because I haven't thought about this now for a minute. Okay, beta. Yeah, in beta minus decay, I destroy a proton. So what actually happens is that a proton becomes a neutron. Um, and in that process, the proton. No, sorry. That is beta plus? Oh my gosh. Oh no. I used to teach this. What is happening? So in beta minus decay. Yeah. 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 In beta minus decay, okay, ignore what I said before this. I might remember to edit this and cut it out. Okay, in beta minus decay, we emit an electron. A beta minus particle is an electron. So where did that electron come from? So in the nucleus of the atom, a neutron we destroy a neutron and it turns into a proton, an electron, and an antineutrino, and also gammas. So photons are emitted. So because this is important because that's we have to preserve charge, right? Conservation of charge is a pretty fundamental law when we're talking about nuclear processes. So a neutron has no charge; it's a neutral charge, right? So if I make a positive particle, I have to also make a negative particle. So we destroy a neutron, we make a proton and an electron. The electron is emitted, the proton stays in the nucleus, and we also, in that process, make an antineutrino. So if you destroy a neutron, you make an antineutrino. And in beta plus decay, a proton becomes a neutron, an electron, and a neutrino. So I make a neutron, I make a neutrino. And then the beta plus particle, again, conservation of charge, right? I destroyed a proton, which has a charge of +1. I made a positron, which has a charge of +1. And so that's emitted into space. That's a beta plus particle. So that's how you make neutrinos when you make a neutron. You make an antineutrino when you destroy a neutron. That's how I remembered it. Anyway, so geoneutrinos are a way to measure the radioactivity of Earth. And again, neutrinos interact with almost nothing. So when you can detect them, you have to make very specialized instruments to detect them. They give you pretty accurate measurements of stuff. Okay. So inventories of heat producing radioactive elements estimated from rock compositions and from geoneutrino measurements. Okay, so we're saying that we can estimate how much radioactive stuff is in a rock based off of a geoneutrino measurement. So that makes sense to me. That I agree with that. because we can measure the decay rate. You should be able to measure the decay rate for beta decays with those geoneutrino measurements at least. Yeah. Okay. Confidence. Lending confidence to the anticipated process. Okay, so we have these measurements and we want to use them to measure, to estimate the heat load due to accelerated nuclear decay during the flood. Again, we've never observed accelerated nuclear decay. So there are two different types of nuclear reactions: spontaneous nuclear reactions and induced nuclear reactions. Induced nuclear reactions, you can absolutely induce at different rates, but that's not what we're talking about. We're talking about spontaneous nuclear reactions. These are ones that just happen in the wild without anybody messing with them. And even when you do mess with them, you can't, right? They're bully proof. They just sit there and keep doing their thing, keep decaying at their constant rate. The one potential exception that comes up uh, in young Earth creationism circles is electron capture. So electron capture is a type of, it's labeled a spontaneous reaction because it's not caused by like an external particle coming in and causing stuff. What happens in electron capture is that if you have lots and lots and lots of electrons in your electron cloud orbiting the nucleus, sometimes a low energy orbit electron can get sucked into the nucleus, right? So it's labeled a spontaneous reaction because it's all happening. We start with just the single atom and no external particle coming in. But if you're thinking about it as particles interacting with just the nucleus, there is an external particle coming in. So electron capture is kind of this middle case. You could make an argument for labeling it an induced reaction, and you could make an argument for labeling it a spontaneous reaction. And this reaction, you can slightly affect the rate at which it happens. I think with like temperature and pressure. I think that's what it is. But it's like humans in a lab have been able to affect that rate to some degree. Notably, that is not a reaction. Because that is true, that electron capture is not a nuclear reaction used for dating purposes. So the nuclear reactions that we use to radiometrically date things are not affected by, as far as we can tell, anything. Decay constants are constant, and nothing any living scientist has come up with has been able to figure out a way to change those rates. So, okay. So this accelerated nuclear decay is impossible based off of everything we know about physics and everything that we have tested about physics. Okay, so preliminary estimates for granite suggest that this radiogenic heat load would be overwhelming without the operation of a powerful in situ cooling mechanism, which has yet to be identified. This is a true statement, and it's just kind of an underwhelming one, right? Like reading the statement, what is it like? Uh, uh, it's like saying, I don't know, uh, yes, the hurricane was associated with cloudy skies, right? It's like cloudy skies doesn't quite capture the hurricane, you know? So there's, yeah. So by the way, granite has a good amount of uranium in it. Fun fact, there's I think it's a baseball field built in, I think, New York. It's a big city that's far away from me. So I don't remember where it is. But ticket takers at that stadium that is built out of granite, that granite had like an extra lot of uranium in it. And so they were, at least for a while, at least in 2012, they were, by profession, the profession exposed to the most radiation. more than nuclear workers, more than airline pilots, right? Ticket takers at this stadium were exposed to more radiation than anybody else. And if that scares you about going to a stadium, that's not the correct response. The correct response is, oh, so even airline pilots aren't exposed and radiation workers aren't exposed to that much radiation. That's the correct response. Um, Kind of like the reason we don't use the banana scale of radiation exposure is in the general public is that people realized this won't make people less scared of radiation. This will just make people scared of bananas, which is why science communication is important. Okay, I'm gonna check my code again really fast. You guys are cool. Thanks for hanging out. Oh my gosh, we're up to 2008 out of 2022 because I don't have atmospheric data for 2023 yet. Okay, so we've read the abstract. Let's see if we can get into the introduction. I'm just going to keep recording as long as my computer's working real hard. And let's see how far we get, and maybe I'll cut this into more than one video. I don't know. So, chapter 7 and 8 of Genesis describe the catastrophic flood, global flood, which God brought about at the time of Noah as judgment upon an incurably wicked human race and our environment. Oh, oh, good. By the way, wait, I guess our citation here is chapter 7 and 8 of Genesis. I feel like you should have to give more specific citations for because it's a lot of claims in there. I'm going to critique this like it is a science paper. Um, like this in at the time of Noah, I would want a citation here. As judgment upon an incurably wicked human race, I'd want a specific citation here, and our environment, I'd want a specific citation here. I'd want specific like chapter and verse for those. Okay, this flood was of such scale and intensity that it must have drastically reshaped the face of the earth and deposited enormous quantities of heat. Cool. I'd actually like to see a citation here too towards like a calculation of that heat, right? Uh, it must have drastically, right? Like that sentence implies prior literature, so there should be a citation there. Since Noah, his family, the animals on the ark, and many aquatic creatures survived the flood, the atmosphere and oceans could not have been heated beyond biological endurance limits. That's probably okay without a citation. That's kind of like it's common knowledge that humans and animals exist, so you don't need a specific citation. The resulting scientific problem is to explain how the heat was removed without raising environmental temperatures too high. No, this is a bad sentence. The reason this is a bad sentence, right, is there's a built-in assumption to it, right? The built-in assumption is that the flood happened, right? Because when we're doing science, we have to be open to all possibilities, right? It's like that, whatchamacallit, Sherlock Holmes quote. Yes, it is Sherlock Holmes. I thought it was Spock there for a second, but that was Spock quoting Sherlock. So Arthur Conan Doyle is who we're referencing. That when all when all other solutions have been eliminated, the result, however improbable, must be true, right? And so if you really wanted to write this as a paper, right, what you would need to say here is that there really are two answers. Either there was no flood, right? Um, or or all of that heat was removed, right? Both of those are potential outcomes with coming into this problem with minimum assumptions, right? Okay. This series of articles seeks to identify and, where possible, quantify the sources of flood-related heat in order to provide boundary conditions and guidelines for creation scientists seeking suitable explanations for how flood and post-flood environmental temperatures were kept within limits. I'm fine with that. And notice he does specifically say here for creation scientists. Right, so he is stating that he's working within this specific worldview. that the flood happened. Um, and yeah, is trying to get some like numbers onto stuff for people to work with. So how much heat did we have to lose is kind of the question, right? How much heat did we have to lose? Since some of the key background literature arises from the RATE, Radioisotopes and the Age of the Earth project, the relevant RATE results are reassessed, partly to place on record an independent appraisal of RATE and some of the ensuing published exchanges. By the way, this should have, we should see a citation here, right? I should see, obviously he's referencing rate, but I should see a citation to specific papers. That's what, especially in the introduction, you should be seeing citations almost every sentence. Because this is assuming familiarity and access to those papers, right? Which is a silly thing to assume. Don't assume that. Just tell me what it is. Okay, this article, part 1, deals with boundary conditions relevant to modeling the Earth's thermal history. That's going to be like that 13 degrees Celsius, right? It couldn't have been warmer than this much. These include its internal temperature field, mantle structure, past and present ocean temperatures, surface heat flows, and its inventory of heat-producing radionucleotides. Okay, so all the stuff we're going to try to consider. Given that several ocean temperature indicators are in current use, we focus here on ocean temperatures reconstruction from oxygen 18 data. That should be a citation. Whose oxygen 18 data? What is the data set that you were using? That needs to be cited. Part 2 deals with newer, less familiar indicators, including minor and trace element ratios, biomolecular indices, and clumped isotopes. I don't actually know what most of those are, so that'll be fun. I've downloaded parts 2 through 4 as well. Part 3 reviews vapor canopy models, which are typically characterized by high pre-flood atmospheric temperatures and a large heat load produced by collapse of the canopy at the beginning of the flood. We've got to reread that. What does that mean? Vapor canopy models. Okay, so this is the idea that in the Bible, there was like all this water in the air that just was up there. That's like an interpretation of the firmament. Okay, so they're gonna have to lay out a vapor canopy model and explain all of the dynamics of it to me. Thanks. High pre-flood atmospheric temperatures and a large heat load produced by collapse of the canopy. Yeah, because if it's vapor, so we have gas. Yeah, so this is a latent heat problem. So if we have all this water vapor, so water in a gaseous state, and then it starts to rain down, right? So we're taking water from its gaseous state, a highly energetic state, to a lower energetic state, to a liquid, right? So it has to give that heat, give that energy somewhere, right? That energy doesn't just disappear because conservation of energy. So that is another source of heat, right? Uh, the water vapor loses heat when it condenses to a liquid. And so it would give that energy to the atmosphere around it, causing it to warm up. This is the opposite of like evaporative cooling. So that you can notice, so you know, when it rains, you're like, the act of raining cool the atmosphere. That's evaporative cooling. Or that's also how sweating cools you down, right? You make sweat, evaporates off of you, and then you cool off because of evaporative cooling. So in that case, you're going from liquid, a low energy state, to a gas, a high energy state. So to get there, the liquid has to take energy from the environment to evaporate. And so that removes heat from the environment or your skin, right, and cools you off. So that's this is that process in reverse. So I'll be excited to read part 3 because that's atmospheric stuff that I know a whole lot about. Right now, I know more about it than I care to. Guys, PhDs are hard. Okay. Part 4 assesses the heat released in catastrophic plate tectonics, currently one of the most successful approaches to flood modeling and in similar flood models. Yeah, that's again enough energy to melt the earth, melt the granitic crust. It's going to melt it. Okay, here the heat problem is caused by the large quantity of hot mantle material surfacing in a short time. No, that's not true, right? Maybe it is. Maybe that's part of it. We'll have to read that part. But just the plates moving generates enough friction to melt the earth. Part 5 addresses probably the most acute flood-related heat source, accelerated nuclear decay, which has been invoked to explain. Oh, by the way, this catastrophic plate tectonics. There should be a citation there. Um, uh, Maybe I should be editing that. No, it's fine. I was like, I should be like making comments and editing in it. It's like I don't want to. I'm gonna have to do that with my dissertation here in a minute. So we're doing this for fun. Um, yeah. Okay. Um, accelerated nuclear decay. This should have a citation, right? He's referencing a process that clearly is been discussed in the literature, right? And so should have a citation to a paper or 5 that talks about it. Which has been invoked to explain several key rate findings. Again, that should link to a specific paper. This heat source was recognized by rate authors. Finally, we get a citation. Yeah, by the rate authors. Okay. Part 5 also reassesses the methods and results of 3 components of rate vis-a-vis, I think, radio halos in granites, fission tracks in zircons, and helium diffusion in zircons. I've actually talked about all those things at different places on my channel, but that'll be interesting. So that's just when he's just laying out what the next parts are going to be. That's fine. Hold on, I've got a code. We're up to 2016. Oh my God, guys, it's going to be fine. And then I have to rerun that code 2 more times today. So it's going to be so great. Okay. No, it won't be that much because those are the winter ones. And there's twice as many winter ones ish as there are summer ones. So the summer ones should go faster. Okay. Several authors have suggested that during the flood, the Earth must have suffered a major bombardment from space. Citation needed, right? There should be a citation right now. Who are these authors? Where did they publish? Where can I go read that? Because I shouldn't have to take your word for anything. The resulting surface heat load is assessed in part 6. Part 7 summarizes our conclusions and suggests possible directions for future investigations, which might reveal a solution to flood heat problems or to clarify key related questions. Okay, cool. So we got through the main part of the introduction. If this was a regular paper, this interior temperatures of the structure of the Earth, that's still introduction, right? So it's actually interesting to me now that we've read that introduction is there is no does he mention an experiment? So normally the way papers are laid out, unless it's a review paper, and I'll mention that in a second, but like um this should just be setting up an experiment, right? This is the open question. Where did the heat go? What are the boundary conditions for thermal blah 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 blah. Um, this is the general background, and then um, this is how we're going to address that specific question. What is the thermal boundary condition, right? But he hasn't actually set any of that up. So I'm going to kind of look for like this interior temperature and structure of the Earth in a normal paper. This is still part of the introduction. That's just background information. So I'm looking for principles of oxygen isotope paleothermometry. Fun. So this is still talking about other people's work, right? On preservation of oxygen isotopes, vital effects. It's going to be marine organisms. This is all like background. Seawater, oxygen 18 levels, appraisal of that data. Oh, hey, look. I've used this. This is paleoclimate. It's a reconstructed paleoclimate data set. That's really cool. The real paleoclimate data set is very, very cool. Um, and he's potentially using the real figure because this has ages in millions of years. Cool. Um, okay. Sorry. It's backwards from the time is moving backwards from what I expected. Okay. Yep. This is all other people's data. Interpretation of the data in terms of flood geology. So this would be their stuff in theory. Um, Surface heat flows. Okay, so let's assume this is a review paper. One, there should be way more citations then. Because in a review paper, that's hey, this field has been going on for a while. I'm going to collect everybody else's data and put it all in one place, right? And talk about the overall picture, overall, where is the scientific community at for this thing right now? And so review papers are going to come out every, like, I don't know. I don't want to put a number on it because then it'll be wrong for some instance, but like 10, 20 years, like, hey, let's collect 20 years worth of data, if it's like a slow moving field or something like that, you know? But review articles are really helpful if you're trying to learn about something new because they're generally like you're not having to mess with all of the technical specifications of an experiment. You're just kind of getting all of the results in one place, which is nice. By the way, if you are like a layperson reading into a field, and by like a layperson, I mean like a layperson in that field. So if I was going to go read a biology paper, right, I would not read the methods. I honestly wouldn't. I would probably read the abstract and the conclusions and see where I got from there. And maybe read the results. Maybe read the results, maybe read the introduction. But that would be it because the methods are going to go over my head because the method section is put in there so that uh, other people in that field can, in theory, reproduce the results. Okay, so we've been talking for about an hour, which is really cool, and we got through the introduction. And so I think I'm going to stop here, and next, like journal club, we'll pick up on interior temperature and structure of the Earth. That sounds fun to me. Okay, so team, I really liked making this video today. That was really fun. I hope I can keep doing this. And we'll just have to see, right? I'm sorry I'm being so inconsistent. Doing my best, got a lot going on, but I miss doing this. So anyway, you guys are really cool. I hope you're doing well, and I'll see you next time. Okay, bye team. End recording.